Okay, welcome in. We're in Module 3, and we're going to be talking about number theory with prime numbers and composite numbers. So here we go. Natural numbers are just the set of natural numbers given by 1, 2, 3, 4 counting numbers, right? If we take any of those two numbers and multiply them together, so like down here, 2 times 12, 2 is a natural number, 12 is a natural number. The result of that multiplication is also a natural number. The two numbers that we multiply are called factors, and the result of that is the product. When we talk about divisibility, if A and B are natural numbers, A is divisible by B if the operation of dividing A by B leaves a remainder of 0. Right? B is a divisor of A, is what we would say, or B divides A. And then we can rewrite that very symbolically here as B with a straight line divides A, right? For example, 12 divides 24 because 24 is divisible by 12 evenly. There are some rules. These are a couple of rules for divisibility to find out if something is divisible by a number. For example, 2. 2 is probably the easiest. A number is divisible by 2 if the last digit of that number is even, 0, 2, 4, 6, or 8. Right? 3 is a fun one. This works for 3. We'll find one very similar for 9 in a moment. But the sum of the digits in a number, if they're all divisible by 3, that number itself is divisible by 3. And so this 5, 2, 3, 4, 1 is divisible by 3 because if I take 5 plus 2 plus 3 plus 4 plus 1, I get, well, 5 plus 2 is 7, plus 3 more is 10, plus 4 is 14, plus 1 is 15, and I know 15 is divisible by 3. If I didn't, I could do this trick again. 1 plus 5 is 6. 6 is divisible by 3, therefore 15 is divisible by 3, and therefore 52,341 is also divisible by 3. Divisibility by 4, you just have to check the last two digits. If the last two digits are divisible by 3, sorry, not 3, but 4, then the number itself is divisible by 4. So this number, 3,947,136, I just have to check, is that last two digits divisible by 4? If it is, then the entire number is divisible by 4. And 5 is another easy one. Things are divisible by 5 only if they end in a 0 or a 5. Some other ones like 6, not as easy. The number 6 is divisible by, sorry, if something is divisible by 6 if that number is divisible by both 2 and by 3. Right? So 954, that's even, so I know it's divisible by 2. Got it. It's divisible by 3 because 9 plus 5 plus 4 is 18, which is divisible by 3. 3 divides 18. So it's divisible by both 2 and by 3, and therefore it is divisible by 6. With 8, 8 is similar to 4, but just a little bit different. We have to check 3 digits for 8. So we check the last 3 digits, 832, divisible by 8. That one is still not that obvious, but something is divisible by 8 if it's divisible by 3. Sorry, if it's divisible by 2 3 times. So 832 divided by 2 gives me 416. Divide it by 2 again, that gives me 208. And divide it by 2 again gives me 104. I was able to divide it by 3 twos, and therefore that was divisible by 8. I just had to check the last 3 digits, so the whole thing is divisible by 8. Now this works for the rule for 3 is similar to the rule for 9. You just have to check to make sure that the sum of those is divisible by 9 to make sure that the number itself is divisible by 9. So for example, 5 plus 3 plus 4 plus 6 is 18, and 9 divides 18. So this number is divisible by 9, right? We just have to be careful because 123, if I check for 3, that's 1 plus 2 plus 3. That's 6, and 3 divides 6, so this is divisible by 3, but 9 doesn't divide, and we would write that like 9 with the division sign, the divides sign with a slash through it. 9 doesn't divide 6, so 123 is divisible by 3, but not by 9. And then for 10, 10's a nice easy one, and number is divisible by 10 if it ends in 0, and that's it. That's the only criteria. Divisibility by 12 would be something that's divisible by both 3 and 4. Right? There's another one. They typically skip it probably for good reason, but there's other ones for 7 and 11. They're pretty ugly, and they depend on some, pretty interesting number theory. Look them up if you feel inclined to do so, but they exist. Anything else that's not on this list, if you need to figure out if it's divisible by it, it's probably quicker just to do the division and see if you get a remainder. So, excuse me, we'll move into prime factorization. A prime number is a number that's greater than 1 that is only divisible by 1 and itself. So like the number 2, right? We immediately exclude 1 from this by saying that the prime numbers have to be greater than 1. But 2 is prime because it'll divide it, it's divisible by 1 and it's divisible by 2. A number like 3 is also under that criteria. I can divide 3 by 1 and by 3, and that's it. So if it's just 1 in itself, it's a prime number. 4 is not. So I'm going to put not, that's supposed to be an N, not prime, or 4, because 2 divides 4, right? But 5, when we get to 5, it's prime again. 6 comes back over to the not prime because it's divisible by 2 and 3. Right? And then these numbers go on and on. We can classify every integer, every natural number as either a prime or these not prime numbers. These are called composite numbers. And that composite number is a natural number greater than 1 that is divisible by a number other than itself and 1. And then our fundamental theorem of arithmetic says every composite number can be expressed as the product of prime numbers in one and only way. And usually up to order is included. And I'll explain what that means in a minute. But there should be one unique way of listing prime numbers out to create any composite number. So one way to find this unique factorization is using a prime tree. So if I take the number 700, I can say whatever 700 is divisible by, I know it's divisible by 7. So I'm going to factor out a 7. If it's a prime number, I'm going to circle it. And then the result, if I take 700 divided by 7, the other factor of that is 100, which is not prime, so I'm going to keep factoring that. This 100 is divisible by 2, which is a prime, so I circle it. The result of that division gives me 50, which is not a prime, so I keep going. I can divide out another 2 and get 25, and then from that 25, I get 5 and 5. Those are all primes, and so I'm done. When the branches, every single branch of my tree terminates in a prime, then I know I'm done. Now, I'd mentioned back here about up to order. I can write this in several ways. I can write this as 7 times 2 times 2 times 5 times 5, right? Or I could write this backwards and I can go 5 times 5 times 2 times 2 times 7, but these are not unique. This and this is the same list of numbers. And it's got the same number of each numbers. There's 2 2s in both and there's 2 5s in both. So what we would do is write this in order of increasing prime numbers. So I would write 2 first, and I would write it in exponential notation. So it's 2 squared because there's 2 of them. And then the next highest prime is 5, and there's two of those, and then there's a 7. And this will be unique. When you order it in this way, every time you break down 700, you'll get this list of primes. And they've done that here. So they've written it one way, and then they've organized it, arranging them from least to greatest, and this will be unique. Meaning you can't break down 700 some other day and get a different list of numbers. It's not going to change on us. It'll always be this. You can't have your friend do it a different way and have them end up with something different. It should come down to the same list of numbers every single time. So let's go on to something called the greatest common divisor. Excuse me. So to find the greatest common divisor of two or more numbers, we're going to write out the prime factorization of each number and then select each prime factor with the smallest exponent that is common to each of the prime factorizations. And it's okay. This is the list of stuff we're going to do. We'll go through it and do it. So if this is confusing, give it a few seconds. We'll jump into it. Once we've done that, from the product of the numbers from step 2, the greatest common divisor is the product of all of these numbers, these factors. Pairs of numbers that have 1 as their greatest common divisor are called relatively prime. So say, oh, there's an example here, 5 and 26. 5 is only divisible by 1 and 5. 26 is not divisible by 5, so the greatest common divisor would be 1. Therefore, 5 and 26 are relatively prime. So let's see an example of this. Let's take 216 and 234. We'll break them each down. I won't do it because it's done here, but 216 is divisible by 3 2s and then 3 3s. Likewise, 234 can break down. It's divisible by 2 and then 3 and 3 and 13. So the very first thing that I want to do is to write each of these 216 and 234 in their prime factorization with smallest numbers first. But I'm also going to take time, and you don't have to draw these out. I'm just going to draw them for illustrative purposes here. I'm going to make sure that each one of these columns has a prime number in it. And so like 216 has 2 and it's 2 to the third. So I'm going to take a moment and check if 234 has any 2s, and it does. It has a 2. I'm going to make sure that this is my 2s column. And then the next one's going to be 3s if they have any 3s. So 216 does. It has 3 3s, so 3 to the third. 234 has 3 squared. And then I'll move on. There would be 5s if there were any down in this column. There aren't any. The next one actually that I have is just the 13 from 234. So I'll write them that way. I'll make sure that they're in a column so that I can compare how many 2s I have for my 216, how many 2s do I have in my 234, right? And then my greatest common factor, I wish I had some more room here. My greatest common divisor is going to be the lowest power of 2s multiplied by the lowest power of 3s. Right? So if I compare the two, I've got 3 to the third, I've got 3 to the second. It's the smallest power, 3 to the second. And then the smallest power of 13s. And if there isn't one, I don't include one, right? So that's it, just the smallest power. So that's a 2, that's 3 to the second, and I multiply those together. 3 to the second is 9, times 2 is 18. So my greatest common divisor, or my greatest common factor is also called, is 18. And we see on this next slide, they've kind of just done that work out. And again, they've ended up with the same value, 18, by finding the lowest powers of every prime in these numbers. Next, we move to something called the least common multiple. The lowest common multiple or the least common multiple is the smallest number that is a multiple of both numbers. So for example, I want to find the lowest, a lot of times you'll see an LCM of two numbers. The lowest common multiple of A and B is the smallest number that A is a divisor of and B is also a divisor of. So for a very simple example here, if I take the lowest common multiple of 2 and 3, that would be 6. Right? And the way that I can find this, there's two ways of looking at this. I can list out those numbers. So I can take, say, 2 and just start listing out multiples. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 6, 2 times 4 is 8, 10, 12, so on. And do the same thing with threes. 3, 6, 9, 12, 15, and so on, right? But 6 is the first number that shows up in those lists. And that's a very perfectly valid way of finding these, but it can be very long. If you have just the right combination of two numbers, you might have to list these out 20 or 30 long, or if you have the lowest common multiple between three numbers, it becomes an extremely tedious process. So there's a better way, a different way. It's not always better, but and by which I mean it's not always faster, but it will catch all of them and it will simplify the really ugly ones. So let's look at that. For this, we want to find the lowest common multiple of 144 and 300. So right off the bat, if I take that first method, I'm already doing calculations I don't really want to do. 144, 288, then 144 times 3 ends in a 2, and then a 3, and then a 4, so 432, I think. 8, 3, 4, yeah. So it's already hard. I don't even want to continue this because yuck, right? So the other way is to list them out by their prime factorization, right? So I'm going to throw this method in the garbage. It's going to take me quite a while to do it. And in fact, when you see the end result here, you'll probably agree that would have taken us way more time than we want to spend. So I write out these factors. And again, when I write this, I'm going to make sure that I do them in columns. So 144, I'm going to write as 2 to the fourth. 300, I'm going to write as 2 squared. And then just right on top of each other, there's a 3 squared in 144. There's going to be a 3. And then off here, there's 5 squared. They sort of tried to do that here, but it's hard to get those to line up when you're typing this stuff. So when I go through these, when I find the greatest common factor, I'm looking for the lowest power. When I'm looking for the least common multiple, I'm looking for the greatest power of each of these. So the highest power of 2s is 2 to the fourth. The highest power of 3s is 3 to the second. The highest power of 5s is 5 to the second. If there's not a 5, it's considered to have a 0, but we're looking for the greatest power this time, so I use that 5 to the second. So my lowest common multiple here is the product of those things. It's the highest power of 2s, which is 2 to the fourth, multiplied by the highest power of 3s, which is 3 squared, and then multiplied by the highest power of 5s, which is 5 squared. And I'll multiply those out. This 2 to the fourth is 16. 3 to the second is 9, and then 5 squared is 25. And all of this multiplies to give me 3,600. And it would have taken us a while to write these out. If I were writing 144, 288, 432, so on, so on, so on, it would have taken me days to get to 3,600. And then I would have also had to have gotten there with 300s as well. So this saves an incredible amount of time. And that's my lowest common multiple. If you listed them out, that would be the first one that appears in both lists. But again, that list is ridiculously long. Don't do that. And this is just the rest of that problem. Let's take a look at an example here. A movie theater runs its films continuously. one move, which means, I mean, this is not a real world scenario, but it means as soon as that 80-minute film is done, it starts right back up and over. So it's on loop, right? And a second runs for 120 minutes. Both movies begin at 4 p.m. When will the movies begin again at the same time? Right. So what we need to figure out is how many times that 80-minute movie is going to play before it starts at the same time as the 120-minute movie, right? So we want to find the LCM of 80 and 120. So I want to find the prime factorization of both, right? To do so in this ridiculously white space-free slide, I would take my 80, divide it by 2. That gives me a 40. That 40 is divisible by 2, giving me a 20. That 2 is divisible by, sorry, that 20 is divisible by 2, giving me a 10. That 10 is divisible by 2, giving me a 5, right? So 80 is 2 to the fourth times 5. And I would do the same thing with 120. I'll spare us trying to do this kind of math in this teeny tiny margin. It's done here. 80 is 2 to the fourth times 5. 120 is 2 to the third times 3 times 5. So again, just if with my whatever you want to call it, my OCD-ness, my need for organization, whatever you want to call it, I'm going to write these in order. So I've got 2 to the fourth. My 4 kind of looks bad. On the bottom, I've got a 3, but on the top, I don't. So leave it blank or draw a square or whatever you want to do. But then I have a 5 on those, right? So they're in order. I'm going to pick out the highest power. So that is 2 to the fourth. That's including a 3. And if you've got a 5 and a 5, it doesn't matter which one you choose. The highest power is just to have the 5, right? So I end up with 2 to the fourth times 3 times 5. So that's 240. That means after 240 minutes, both of those movies will be on their starting point simultaneously again. So if we started at 4 p.m., 240 minutes is 4 hours. So they'll start again 4 hours later, which is 8 p.m. That's it. Thanks for hanging with me. Thanks for being here. Check out the other videos, and I will see you guys next time.